Okay, class, so we start with multivariable calculus in section 9.1. And multivariable calculus, we are doing calculus and many applications in three-dimensional space. So in the past, you have worked, for instance, with the two-dimensional space, the XY planes. But now in our multivariable calculus, we're dealing with three-dimensional space, and so we need three axes. So you see here, this is standardly how we do it in this class. We have coordinate axes. The x-axis comes out in that direction, the y-axis comes out in the direction you see, and the z-axis comes out vertically. Okay, this is how we do it in our class. And if we think about the x, y, and z axes, it cuts up three-dimensional space into how many octants? How many octants are there in three-dimensional space? That's right, Grayson, there are 8. Very good. So in calculus 2, you had the xy coordinate plane and two axes, the xy axes, broke that coordinate plane up into 4 quadrants. But now in multivariable calculus, we have these 3 axes that are at right angles to each other. They break up the space into 8 we call them octants. Okay, 4 above the xy plane and 4 below the xy plane. Now, what am I talking about here? XY plane. Well, if we go down, hold on, I went down a little fast. If we go to here in figure 3, you see there how on the picture to the left, you have an XY plane formed by the X and Y axis. You have the YZ plane formed by the Y and Z axis, and then the XZ plane formed by the X and Z axis. Okay, so those are your what we call our coordinate planes. Our coordinate planes. Okay, are there any questions on those? They divide the space up into the 8 octants. Okay, let us proceed on here. So figure 4. Now figure 4, how do you plot a point in three-dimensional space? Well, you see that point P has coordinates A, B, and C. Okay, those are your coordinates of P. The A is what's called the X coordinate. So you see you start from the origin, that in figure 4, that's where the O is, at the origin. And you move forward a distance. If A is positive, you move forward a distance of A. Okay, and then if the B coordinate, which is the B is the Y coordinate, if that is positive, you move to the right in the positive Y direction, a distance of B. And then if this C value, which is the Z coordinate, okay, that's the third coordinate, if that's positive, then you go up a distance of C. And this is how you plot points in three-dimensional space. So they have some examples here. We go down here. The book has very nice examples. Okay, figure 5 is nice, but let's look at figure 6. Figure 6, they have 2 graphs. The first graph on the left, they're plotting the coordinate, they're plotting the point with coordinates -4, 3, and -5. Okay, and you see how you start from the origin, and since the x coordinate -4 it's negative, you don't go in the positive x direction, you go in the negative x direction 4 units. And then the y coordinate is a +3, so you move to the right 3 units. And then the z coordinate is -5, so you go down 5 units. And that's how you plot the point. And then they plot the point 3, -2, -6 on the picture on the right. Okay, are there any? So sometimes with sometimes, I mean, I have my own examples I like to do, but these are fine for this material. So I'm giving you a little bit of a guided tour. Are there any questions so far? Okay. Okay. Well, let us proceed on then. Let us proceed on. So in example 1, they would say what surfaces in R3 are represented by the following equations. So in example 1, when they have that letter R, okay, that script R with a 3 there, that means three-dimensional space. Three-dimensional space. In other words, this here, that's just a symbol that means three-dimensional space. And they're wondering, okay, what surface is represented by the following equations? Z equals 3. So if Z equals 3, well, I mean, when we plot coordinates in space, we have an X coordinate, a Y coordinate, and a Z coordinate. What's always true about the Z coordinate? If we're going to plot the surface Z equals 3, what's always true about the Z coordinate? What must it equal? That's right, Matthew. The Z coordinate has to equal okay. Z coordinate's 3. Z coordinate's 3. So let me go to the whiteboard real quick here. Hold on. So, okay, so any surface in space, okay, I mean, the surface consists of points, right? So if Z equals 3, if Z equals 3, then that means that the Z coordinate here has to be 3. But X and Y can be anything. Because if Z equals 3, you can think of it like Z equals 3 plus 0 times X plus 0 times Y. Okay, so for instance, the coordinate 0, 0, 3 is on this surface, Z equals 3. That's a point on the surface. The coordinate -1, 2, 3 is on this surface. The point 20, 5, and 3 is on this surface. So long as the Z coordinate equals 3, the point is going to be on the surface. So what do you think is going to be traced out? If you had to describe this surface Z equals 3, if you had to describe it, what would it be in three-dimensional space? What would it look like? That's right, Lexi, a plane. Very good. And if we go back to the example, in figure 7 on the left, that's the picture of Z equals 3. It's a horizontal plane, 3 units above. And that's right, Yeva. It's an infinite plane parallel with the XY plane. That's right. That's what Z equals 3 looks like. Now, if we consider the plane y equals 5, if we consider that one, okay, so you're used to thinking about y equals 5 as a horizontal line, right? That's like in two-dimensional space, y equals 5 is a horizontal line that's 5 units above the x-axis. But in multivariable calculus, y equals 5 is actually a vertical plane. It's a vertical plane where if you look at that second picture there in figure 7, every point on that plane has a y coordinate equal to 5. Now the x and the z coordinates vary, okay, but the y coordinate is going to equal 5. That's going to trace out that vertical plane. Okay, you see how that works? Are there any questions on that? Okay, so we have to now start thinking, you have to start thinking three-dimensionally. Okay. All right, and that's good because, you know, in life, phenomena usually occurs in three-dimensional space, right? All right, let's go look a little bit more here. Okay, so this example, what points are satisfy the equations x squared plus y squared equals 1 and z equals 3? What would that look like? What would that look like? So, might be easier to actually look at B first in this. In B, they will say, okay, what is the equation x squared plus, well, hold on. Let me see if I can, sometimes I can highlight it, yeah. What does the equation x squared plus y squared equals 1 represent as a surface in R cubed in three-dimensional space? Well, normally when you see x squared plus y squared equals 1, what would you, like in two-dimensional space, what is that? That's right, Jacob. That's a circle with radius 1 centered at the origin. Okay, but now, what variable didn't they mention in this equation? What variable didn't they mention?
Z.
The z. That's right, Yeva. And so what can z equal?
0.
It could equal 0. It could equal...
Any positive integer or any number?
Well, in fact, let's see here. Let's one moment here. Let me just clear that out. So x squared plus y squared equals 1. That's the same as x squared plus y squared plus what times z equals 1? What number would we have to put here? That's right, Lexi, a 0. A 0. So think of if we were to draw okay, an x, y, and z axis, right? We could draw a circle here, right here, in the xy plane. Okay, we could draw a circle here. and that obeys x squared plus y squared equals 1. If that's a circle centered at the origin with radius 1. But could we draw another circle up here centered at 2? Would that obey? Would that obey? And let's say that has radius 1 also, that circle. Does that obey the equation x squared plus y squared equals 1? Does that also obey the equation? It does. It does. That's right. It does, Matthew. And actually, if I drew another circle below the xy plane, where z is -2, and that circle has radius 1, does that obey the equation x squared plus y squared equals 1?
Yes.
It does. So what are all these circles going to add up to that I'm drawing here?
A cylinder with no top or bottom.
That's right,
Because it's
Mary. That's
infinite.
right, Yeva. That's right, Grayson. Yeah, it's going to be a cylinder. Trace out a cylinder. That's right. With no top or bottom. It goes on forever, but yes. So you see, in calculus 2, you would think of x squared plus y squared equals 1 as a circle. As a circle in the xy plane with radius 1 centered at the origin. But in three-dimensional space, in multivariable calculus, that is a surface. That is a surface. Okay, and you have to be, sometimes these kind of questions in the homework are like multiple choice, so you have to take your time answering them. You have to be careful, but yeah. So for this example here, example 2, here's figure 9. It's a cylinder, x squared plus y squared equals 1. That's just a cylinder. But if we add a constraint where x squared plus y squared equals 1, but z equals 3, then that's going to be a circle, 3 units above the xy plane. Okay. So far, so good? Okay, Yeva. Okay, Aura. Very good. Very good, Mary. All right. All right. Well, let's do a little more here. We're going to take we'll take a break certainly by 8 o'clock. Don't worry. We might just have one break tonight because we went a little bit long on the orientation, but I'm happy about it. We answered a lot of good questions. Simon is Simon's screen is he says his screen's black, but the rest of you all, can you see it okay?
I see it fine.
Okay, so all right, Simon fixed it. Let me see. Ivy says, could you say Z is similar to how? Hold on here, one moment. I'm not looking at my phone. I'm seeing. There's a question here by Ivy. Could you say Z is similar to how Y is in an XY plane? Yeah, I guess you could think of it like that, Ivy. Yeah. And you know what else we can do here? Hey, here's something. So see, here's the plane y equals x. So you draw the line y equals x. Okay, that's a 45-degree line between the positive x and y axes. And you take that line and bring it up and down. Just layer it up and down, you get a vertical plane. And they note here that the familiar distance formula for the distance between 2 points in a plane is easily extended to the following three-dimensional formula. So three-dimensional formula is here. show you if you have any 2 points in space, the distance between the 2 points, 1 and 2, is given by that formula. Might have to sneeze.
Bless you.
Thank you. I have allergies, I think. One moment. Okay. So, yeah. So, and you know, if we were to, well, the distance formula is just an extension of the distance formula you know for when you have the distance between 2 points in the plane. The distance for 2 points between 2 points in three-dimensional space is just that formula. Okay, now they prove that on the next page, but we'll just, let's just, hopefully you're comfortable with that. Something else that's important here is the equation of a sphere. So they say, all right, find an equation. Hold on, let me highlight that. Find an equation of a sphere with center H, K, and L. Okay, H, K, and L. And by definition, what is a sphere by definition? Well, by definition, a sphere is a set of all points whose distance from the center, point C, is R. So that means then that if you take this distance between P and C, points P and C, P is any point on the sphere. The distance between the point P and C would have to equal R. So if you square that, you'll get this formula. If you square both sides of that distance between P and C equal R, you'll get that formula. And so now you have a formula for a sphere. Okay, so these are all pretty good things that you're learning. And let's do an example here. Let's do an example. Let me bring this up here. Let's do an example like this. Okay, one moment. Okay, they want you to find, so what I like to do, this example, so the book has good examples, but oftentimes I like to supplement the book's examples with my own examples. But how many of you are going to put like these? I mean, of course, this example is in the recording, but how many like to copy the example down and put it in like their notes in a notebook and find that helpful? Even though this is a remote class, okay, R likes doing that, Mary likes doing that. Who else likes doing that? Christopher does. And it's a good thing to do, class. Lexi likes that. It's a good thing to do because writing is thinking. So I'd like everybody, very good, excellent, Brand. I'd like everybody to maintain a notebook and take notes. So like the stuff that we looked at was somewhat intuitive, but now here's a problem, here's an example that we're going to do. So let me give you a moment to copy this example down, and then we'll talk about its solution. And this example is not in the book, but you'll see it in the homework, a problem like this. So I want to do one like this. Okay, I'll give you a moment to copy this example down. Okay, okay, good. And Abby, you're with us. Okay, wonderful, wonderful. I've been monitoring my email, and Abby's here. Excellent, excellent. Okay, so what I'd like you to do here is I'd like you to try to figure out the answers to these questions. I want you to try to figure it out, and it could help to, hold on, I'll learn how to do this. It could help you to draw, hold on, get over here, the X, Y, Z axes. I mean, that could be helpful. Some of these, like, yes, you could use the distance formula, but some of these problems, you might be able to intuitively figure out what the distance is. So let's just look at the first one here. We want the distance from the coordinate 3, 7, -5 to the xy plane. 3, 7, -5 to the xy plane.
Is that 5?
That's right. That would be 5. Very good, Mary. You don't even really need to, you don't really even need to use the distance formula. You can, hopefully intuitively, you can see that. So the xy plane, right, is, you know, there. And this coordinate here is 5 units below the xy plane. Yes, the 3's there for the x coordinate and the 7's there for the y coordinate. But wherever that point is, and it's going to be in this octant in the front here below, it's going to be 5 units below the XY plane. So the answer is 5. See, that's what I'm hoping, particularly for the first 3 ones. Well, IB, distance has to be positive. Distance has to be positive. So that's why we say the distance is 5. Good question. Good question. Okay. All right. So let me give you just a little time here, and let's see if you can figure these out. And then I'm going to put up the answers. Okay. All right. Very good. And feel free to chat. Use the chat feature there if you need to. Gabe had a question on parts D through F. No, for those, use the square root answer. WebAssign, by the way, wants exact answers, like with square roots and so forth. So like for trigonometry and so forth, you use, and whatever else, use simplified radical answers. The only time it wants decimals, WebAssign, is when it says like approximate the answer. Also, too, WebAssign, if you ever have an expression where you're using grouping symbols, for WebAssign, use parentheses. Don't use these symbols here. You know, don't use that. Now, it's okay if you're talking an interval, but don't use that for grouping, and don't use the brackets for grouping. WebAssign wants parentheses. All right, a little more time here. Let me see, IB. Hold on here. One moment. Good try, IB, but not quite. Good try, but not quite. Lexi, you're good. Your answer for D and E is good, but F is not quite right. F is not quite right. Yeva, that's good. The first answer, that's right. Good, good, very good. Okay, I'll put up the answers in a moment here. Well, now see, Lexi, what would happen on the exam? Like Lexi, I don't think she'll mind me. The last answer for F, Lexi was off a little bit. And so what'll happen on like an exam C is you'd have another try on that, you know, actually a few more tries, right? But I view exams as, you know, I mean, to me it's more about, it's valuable if you get the answer wrong, but then figure out what you did right. I mean, that's valuable, right? I mean, of course, it's great to get it right the first time, but we're humans, you know. So, Arian, I need square root answers. Square root answers. Can you resubmit your answers with square roots on them? We got to think that way because WebAssign will count it as wrong. And a decimal answer, when it wants an exact answer, would be wrong in the homework, but it would be wrong on the exam too. Okay, no problem. That's all right, Simon. No problem. So I like doing this sometimes, you know. Have you figured things out? All right, Ara. Yes, good, good. Yeah, well, all I'm doing, Norina, is some students are sharing with me what their answers are. And let me just kind of put up the solutions here. So hopefully A, B, and C are okay. IB, did you figure out A, B, and C? Did you figure out the B and C there? Okay, all right. So for well, this Ashvia, this is going to be in the recording. I'm making a recording of this. So the way I have it is I don't have like my examples posted as PDFs. They're in the recording, and it's better because I'm talking about them too. But it's in the recording. Let's see here. So for B, why is the answer for B 3? Okay, let's see here. One moment. So B, you want the distance from the point 37 negative 5, which is down here, maybe to the YZ plane. So the YZ plane is, you know, I mean, think about doing this. Move out a horizontal distance till you hit the YZ plane. You're three units away until you hit the YZ plane, because the X coordinate is 3. So that means you are, you know, that's a distance parallel to the X axis. So from the coordinate 3, 7, negative 5, that point to the X to the YZ plane is just a horizontal distance of 3. Now, if you want to go to the XC plane, the XC plane would be about this distance, right, to the XC plane. Now, wait, I don't know why that's doing that. Hold on, I don't know what that's about. Hold on, let me get rid of that. Let's clear that. Let's try that again. Hold on, class. I don't know what it's doing here. Hold on. I hit a button. Sometimes you hit a button and things go a little bit wacky here. I don't know what's going on here. Hold on. Here are the annotations. I just want to use my pen. See how it's making like a brick or something? What is that? Okay, hold on, class. I'll have to let me come out and back in. One moment. Let me go out. coming fresh. I don't know what that's about. I'll have to figure that out, you know. All right, please tell me it'll do this. Okay. So you see IB, so for part C in this problem, you want the distance from the point (3, 7, -5) to the XC plane. To the XC plane. That's that distance, right? That's, I mean, if we think about it, that's this distance here, right? So do you agree then, IB, that that would have to be 7? Because that's the same distance as is this distance, which is 7. You see that? See how I'm doing that?
Yes.
Okay. Okay. That we're really just using. Yeah. Now let's do the part D. D says what's the distance from this point here, 3, 7, -5, to the x-axis. Well, here's the x-axis. Here's the x-axis. So that distance for part D is this distance, right? That's that distance from 3, 7, -5 to the x-axis. So the x-coordinate of 3, I mean, that distance would be from 3, 7, -5 to the point 3, 3, 0, 0. So what you can do is you can create a little right triangle here if you wanted. I don't know why I keep, hold on, I gotta hit a little right triangle here. And this distance here is 7. And this distance here is 5. And so the square root of 7 squared plus 5 squared, right? That's going to give you this hypotenuse here, this hypotenuse distance, which is what you want. That's going to equal the square root of 49 plus 25, which is the square root of 74. Now that's one way to do it. Another way to do it for part, again, we're looking at part D here. Another way to do it is as you see here. Use the distance formula. See? So there are 2 ways to do it. Now for E, part E, if you want to go to the y-axis, right, is the distance from that point to the y-axis is this distance here. Okay? But that distance, again, you can form a little right triangle here. Okay, and this again, got to be a little careful here how I do this. This distance is 5, and this distance here is 3. So for E, we want this hypotenuse distance. For E, that's going to be the square root of 5 squared plus 3 squared. And that's going to equal the square root of 34. See how we're doing that?
Yes. Yes.
Okay, good. So, you don't always have to, we don't always need a formula, or if we can use our intuition, excellent, IB, it's very helpful. Excellent, Simon, excellent. And then, but then of course, if you want to do it like the kind of the old-fashioned way, use the distance formula. And then, F is square root of 58. So, are there any questions? I'd like to do just one more example with you, and then I'm going to put us all on break a little bit here, and I'll open up that first assignment so you can get a start on it. Okay, everybody's good. All right, let's hold on. This is not the. Is this the example I want? Hold on, class. Give me one moment here. This is not actually the example I want. Yeah, this is what I want. Because we did the example like that. We saw one in the book. What I want you to do is take a moment. What does this equation represent? X squared plus z squared equals 9. What does it represent in three-dimensional space? And then draw the surface. Sketch the surface. Okay, let me give you a moment to try that. Okay, I'll give you a couple more minutes here. IB, you're right. You're right. And now see if you can make a little sketch. That's right, Arian. Good. And now see if you can make a little sketch of it, of what this surface is. It's a surface. Okay, here it is. Yes, it's a cylinder. Yeah, we'll finish. So when our break starts, everybody should, the class key for Montgomery College, to get you in WebAssign should be there in Blackboard. It should be there, and it's right there under announcements. And then I'm going to take the password off. But let's see here. So it's a cylinder. How many saw that it's a cylinder that goes through? Very good, Simon. Very good. It's a cylinder that runs down the y-axis. How many? Yeah, yeah. That's right. Very good, Yeva. And you see, if you were to draw a circle, if you were to draw a circle, x squared plus z squared equals 9. If you were to draw that, okay, in the xc plane, this would be your circle, right? With radius 3. But since again, x squared plus z squared equals 9 can be thought of as x squared plus z squared plus 0 times y equals 9. And so y can be anything. So, if y were equal to 8, okay, you could just take that circle and move it 8 units down there. If y were equal to -7, you could just take that circle and move it 7 units to the left, you see? And when you put all the circles together, you trace out a cylinder that runs along the y-axis. Are there any questions on that? Who's feeling comfortable? Who's feeling comfortable so far with this section? Okay, R is wonderful. Okay, Mary and Yeva and Christopher, wonderful, and Simon and Alexander. Hold on, a lot of chats here and a lot of people here. Let's see here. Hold on here. Hold on. Okay, and Matthew, Alberto, Devasina, ID, Norita, Ashish, Angela, wonderful, wonderful. Okay, well then, let me, give me just one moment here. I'm going to go ahead and stop the recording here then. We're done covering section 9.1.